Last video, we went from wave to word, speech recognition. Take an audio waveform and get out a transcript. Today, the opposite direction, text to speech. Take a string of text and get out an audio waveform that sounds like a human reading it. This was one of the ugliest, slowest to improve tasks in the whole field. Synthetic voices sounded robotic for 40 years. And then, in the span of about 18 months, between 2016 and 2018, the whole problem got quietly solved. This is video 8 of lecture 8. We already did speech going in, now we do speech going out, and then the story is a beautiful mirror of ASR, same three eras. Concatenate real recordings, model the spectrum, then generate raw audio samples with a neural net. Once you see the shape, the whole modern voice cloning industry makes sense. Video 7 ended with Whisper, a single model that handles any audio in any language and drops a transcript. In practice, this means you feed it a podcast and it produces the words. Now flip that arrow. If you have the words and you want a podcast, how do you make one? That has been an open problem since the 1960s. Bell Labs made a synthetic voice that could sing Daisy Bell. It sounded like a dying refrigerator. Today's puzzle: why did TTS take so long to sound human? And the answer is, the ear is brutally sensitive to unnatural prosody. You can accept a transcript that's 92% accurate. You cannot accept a voice that's 92% human, because that 8% is exactly the uncanny valley zone. So TTS had to hit a much higher bar than ASR before anyone said this actually works. Today's 3 beats. First, Concatenative TTS. Record a huge database of tiny speech units. Stitch them together for the target text, the 1990s workhorse. Second, Parametric and Tacotron. First, a statistical model of the spectrum. Then, in 2017, an end-to-end neural net that maps characters directly to a spectrogram. Third, WaveNet and the neural vocoder revolution. Plus, what happens after? Zero-shot voice cloning, and where the field sits in 2026. Beat 1. Concatenative TTS. The idea is embarrassingly simple. Hire a voice actor, put them in a recording booth, have them read hundreds of hours of carefully designed sentences, chop the recordings into tiny units, usually diphones, which are the transition from one phoneme to the next. Store all of them in a giant database. Then, at synthesis time, for any target text, you pick the units you need and glue them together. Hunt and Black 1996 introduced the classic algorithm. Unit selection. For any target phoneme sequence, search the whole database and find the set of units that minimize 2 costs. Target cost. How close is this unit to what you actually want? Concatenation cost. How smoothly does this unit join to the next one? Dynamic programming picks the best path. And this works well enough that AT&T shipped it in real products, well enough that Siri and Alexa still used concatenative voices in their early years. The problems with concatenative: it sounds decent for the sentences it was designed for. It sounds terrible when you ask it to read something outside its training distribution. Every new voice needs another 20 hours of studio time. Prosody is stiff. You can hear the seams. And if you want the same voice to sound excited sometimes and sad other times, you basically need to record the entire database again in each emotion. Not scalable. Beat 2. The parametric era. Instead of stitching real recordings, model the sound. Hidden Markov model TTS. For each phoneme, a statistical model predicts the spectral parameters: pitch, form and frequencies, duration. Then a synthesizer, called a vocoder, takes those parameters and generates the waveform. Advantages: one small model instead of a giant audio database. Change emotion by tweaking parameters. Disadvantage: the output sounds muffled, like the speaker is behind a blanket. In 2017, Google published Tacotron, Wang and collaborators. And this was the first paper where a neural net went end-to-end. Characters in, mel-spectrogram out, no phoneme dictionary, no handcrafted linguistic features. A sequence-to-sequence model with attention read the letters like they were another language and generated a picture of the intended sound. Then a separate vocoder turned the spectrogram into audio. The result did not sound muffled, it sounded like a person. Tacotron 2 Shen and collaborators 2018 was the polish. Better attention, cleaner spectrograms, human parity mean opinion scores on many test sentences, Google Assistant, Amazon Polly, most modern cloud TTS APIs, all descendants of this Sec2ICQ idea. The acoustic model is basically solved. What was still expensive in 2017 was turning the spectrogram into actual audio samples. That's the vocoder. And that's where WaveNet comes in. Beat 3. WaveNet, Van den Oord, and collaborators at DeepMind, 2016. Radical idea. Instead of modeling the spectrum, model the raw audio samples directly. Audio is 16,000 samples per second, sometimes 24,000. WaveNet predicts each sample one at a time, conditioned on the previous samples, like a language model, but for waveform bits instead of words. Dilated causal convolutions let it see far back into the audio without exploding compute. The output was indistinguishable from human speech. Original WaveNet was too slow to run in real time. It predicted each sample sequentially, but engineers immediately started chasing the same quality at faster speeds. Parallel WaveNet, WaveGlow, WaveRNN, HiFi-GAN. Each one used a different trick. Flow-based models, GAN training, careful architecture, to generate audio in one shot instead of sample by sample. By 2020, high-quality neural vocoders ran 50 times faster than real-time on a GPU. Where the field sits now. VALL-E, Microsoft 2023. Give it a 3-second sample of someone's voice, and it can read arbitrary text in that voice. Style TTS 2, 2023, does similar zero-shot cloning with clean prosody control. Modern TTS is basically a solved problem for major languages. Small mistakes remain around exotic proper nouns, sarcasm, and languages with fewer training resources. But you can now build a convincing synthetic voice from a 3-second audio clip. That is what it looks like when a task gets finished. 3 takeaways before the quiz. 1. Concatenative TTS records a huge database of diphones and stitches them at synthesis time. Hunt and Black 1996 formalized unit selection. It shipped in real products through the 2010s. Decent quality, stiff prosody, expensive. 2. Parametric HMM TTS was smaller but muffled. Tacotron 2017 fixed it. Characters in, mel-spectrogram out, end-to-end. Human parity acoustic quality on many sentences. 3. WaveNet 2016 generated raw audio samples, one at a time, and sounded indistinguishable from human. Modern vocoders like HiFi-GAN run 50 times faster than real-time. VALL-E and Style TTS2 do zero-shot voice cloning from a 3-second sample. TTS is basically solved. Quiz 1. What does concatenative TTS actually do? A simulates the human vocal tract with a physical model. B records a large database of tiny speech units like diphones and picks and stitches the best sequence for the target text. C predicts one raw audio sample at a time with a neural net. Or D uses hidden Markov models to predict spectral parameters. B. Hunt and Black 1996 Unit Selection Synthesis. Real recordings from a voice actor, chopped into diphones, glued together with a lattice search that balances target cost and concatenation cost. Decent quality but stiff, expensive, and every new voice needs another 20 hours of studio time. Quiz 2. What was the key innovation of Tacotron? A faster than real-time inference on a CPU end-to-end Sec2ICQ with attention that maps characters directly to a mel-spectrogram, no phoneme dictionary or handcrafted features required. C. The first system to model raw audio samples. Or D. A rule-based prosody generator. B. Tacotron and Tacotron 2 are the reason cloud TTS APIs stopped sounding muffled around 2018. End-to-end means the neural net learns letters to spectrogram in one shot. No linguistic feature pipeline. The vocoder step was still separate at that point. Quiz 3. What does WaveNet do that earlier vocoders did not? A runs on smaller devices. B. Models raw audio samples autoregressively with dilated causal convolutions, output indistinguishable from human speech. C. Requires no training data. Or D. Only works for English. B. Vanden Oord and collaborators at DeepMind 2016. Predict each of 16,000 samples per second, conditioned on previous samples. Dilated causal convolutions look far back into the audio without blowing up compute. The original was too slow for real-time. Parallel WaveNet, WaveGlow, and HiFi-GAN made it fast. Back to the puzzle. Why did TTS take so long? Because the ear is unforgiving, and the field had to keep raising its own bar until concatenative gave way to parametric. Parametric gave way to Tacotron, and Tacotron plus WaveNet finally hit human parity. Same 3-era arc as speech recognition, only in reverse. Next video, we leave speech and go back to text. How do you mine a whole field's specialized vocabulary? Term extraction. Next time, term extraction. How do you take a pile of medical journal articles and pull out every domain-specific term? Deep vein thrombosis, angiotensin converting enzyme, TF-IDF, C-value, rake, the classical methods that still run in production. Hit subscribe.